All right, so yeah, Tenzin. Okay, so on Monday we talked about started talking about polynomials, and we talked about end behavior. We talked about finding zeros, which are X-intercepts, and we talked about multiplicities of zeros, and we talked about turning points, those places where you go from increasing to decreasing or decreasing to increasing. So we're now ready to learn how to create a quick sketch of a polynomial function. So we even did a little bit of this on Monday, but today we're just going to formalize it. So if I want to graph x to the fourth minus 6x cubed plus 9x squared, step 1 is going to be determine its end behavior. Okay, so my leading term is x to the fourth, leading coefficient of 1, and the degree is 4, which is even. Okay. So because the degree is even, we know that the end behavior is the same at both ends, either both up or both down, right? Even degree, same end behavior. And since the leading coefficient is positive, both end behaviors are up. Okay, so you need to look at the degree and whether it's even or odd, and the leading coefficient, whether it's positive or negative, and that tells you about the end behavior. So in this case, the graph rises both to the left and to the right as the end behavior. And the notation for that would be as x approaches either positive or negative infinity, the far right or the far left, f of x approaches infinity. So step 2 would be to find the x-intercepts. Those are the zeros by setting the function equal to 0. So we set x to the fourth minus 6x cubed plus 9x squared equal to 0, and we solve it. Okay. Any ideas on how to solve that? Factor out an x squared. So I've got 0 equals x squared times x squared minus 6x plus 9. And then x squared minus 6x plus 9 can factor a little bit more. So this is going to be x squared times x minus 3 squared. And then set each factor equal to 0. So either x squared equals 0, which means x is 0, or x minus 3 squared equals 0, which means that x equals 3. Now, both of those zeros, what is the multiplicity of each of those zeros? 2, yes, because they were factors twice, right? X squared, that means x is a factor twice, so x equals 0 is a 0 of multiplicity 2. And x equals 3, that is a 0 twice because x minus 3 was a factor twice. So x minus 3 also has multiplicity 2. You got it. Okay, step 3, find the y-intercept. It's just 0 in this case, yeah. So you just plug a 0 into the function. In this case, it's 0. And then we want to see if there's any symmetry. Okay, so if this function is even or odd, it can help us draw the graph. So a shortcut for polynomials, remember the definition of even was that f of negative x equals f of x. The definition of odd is that f of negative x is negative f of x. But the reason they're called even and odd has to do with the exponents in polynomials. So for a polynomial function to be even, every exponent has to be even. Okay, so look at the original polynomial, right? Is every exponent even? No. Is every exponent odd? No. Then this is neither even or odd. Symmetry is not going to help us draw this one. Odd, every exponent. Okay, now this shortcut only works for polynomials, so just keep that in mind when we move on to another chapter. This will work. This shortcut is only for polynomials. Okay, last step. Use the fact that the maximum number of turning points of the graph is n minus 1. What is n for my polynomial? 4, right? So the maximum number of turning points I could have is 3. Good. So we want to use that to check whether it's drawn correctly. So I'm going to take all the information I found in steps 1 through 4 to sketch a graph, and then I'm just going to confirm that, oh yeah, I have 3 or fewer turning points, so that's like a good sign that I did it right. All right, so my end behavior is that both ends go up towards infinity. So I'll put in the end behavior at the far right and the far left. Does something like that. All right, and then I'll put in my zeros. I have 0 and 3. Zeros, 3. And those both have even multiplicity, which tells you what is going to happen at those zeros. It's going to bounce. Yep. It's going to bounce off the x-axis. So this is going to come down to my 0, touch it, and bounce. And then it has to come back down and bounce off again and connect with the end behavior. How many turning points does this graph have? 3. Yep. 1, 2, 3. 2 local mins and a local max. So that does confirm this. We have 3 turning points. And in this case, n equals 4. N is the degree. It's the highest power on x. So when you look here, the 4 is the highest power, so it's degree 4. So, yeah, and we call that n. Okay, you try. Go through that 5-step process and sketch a graph of x cubed minus x squared minus 6x. No graphing calculators unless you want to check your graph at the very end. All right, so we first want to find end behavior. So we look at the leading term, that x cubed. It has an odd degree, which tells us what about the end behavior? It is opposite, one arm up, one arm down. Okay. And then to determine which arm is up, right, we look at the leading coefficient, which in this case is +1. It's a positive number, and the leading coefficient tells you about the right arm, right? If it's positive, the right arm is up. If it's negative, the right arm is down. So our right arm is going to be up and our left arm is going to be down. So there's my end behavior. All right, and then we find x-intercepts by setting the function equal to 0 and solving. So we've got x cubed minus x squared minus 6x equals 0. Factor out an x because there's an x in every term. And then that parentheses, that quadratic in parentheses, can factor even further, and that would factor to x minus 3 times x plus 2. And then you set each factor equal to 0 and solve, and we get x equals 0, x minus 3 equals 0, and x plus 2 equals 0, and we get x equals 0, x equals 3, and x equals -2. And what are the multiplicities of those 3 zeros? 1. Because each factor appeared just one time, so these are multiplicity 1, multiplicity 1, multiplicity 1. Y-intercept, compute f of 0. What do you get when you plug 0 into that function? 0. So it doesn't really help me. Symmetry. Okay, is this function even or odd? Neither, because all the exponents have to be odd or all the exponents have to be even. So this is neither. We get no help here. What are the maximum number of turning points I could have? 2, 1 less than the degree. All right, so now I put in all this information that I know. I put in the end behavior, up to the right, down to the far left. I put in my zeros, which are 0, -2, and 3. And I know that they're all multiplicity 1, which means that when the graph comes up to one of those zeros, it's going to pass through the axis rather than bounce off. So I'm going to have my end behavior come up to meet my farthest left 0, and it's going to go through. It has to turn back around to get to this 0, and it's going to go through. It has to turn back around to get to this 0, and it goes through and meets the end behavior. So this is a qualitative graph. We know the end behavior, we know the zeros, we know what it does in between the zeros. But you might have drawn your graph, your graph might look like this. Right? Both of those graphs meet all the criteria of what we've sketched. As of now, we don't have a way to be more accurate, okay? But we can sketch good qualitative pictures. We can figure out where the zeros are, we can figure out where it turns around, and we can figure out its end behavior. All right, how many turning points in both this purple and the green graph that I drew? How many turning points are there? 2, and that's good because that's the most that we can have. Yeah.
Is the turning point always less than the
It's always less than. The most it can be is 1 less than, but it could be less than that. All right, so let's do another one together this time. So this time I gave you the polynomial already factored. I did all the factoring for you. So that means that finding the zeros or the X-intercepts is going to be easier because you don't have to factor anything. So either negative x squared is 0, x plus 2 is 0, or x minus 2 is 0. And in this case, x equals 0, x equals negative 2, and x equals 2. What are my multiplicities of these zeros? First one is 2 because it was an x squared. That factor appeared twice. And the other 2's have multiplicity 1. All right, so that made finding the x-intercepts easy. How about the y-intercepts? Is it hard to plug 0 in? Yeah, you're going to get 0 times 2 times negative 2, which is 0. So f of 0, you just plug it in and get 0. All right, so let's go back to end behavior now. I skipped it on purpose because now it takes a little bit more work to determine the leading term. Okay, I need to figure out the degree of the leading term and the coefficient on that leading term when it's all multiplied out. So I could do all the multiplication, right? I could FOIL the x plus 2 and the x minus 2 and then distribute a negative x squared. Or you could just imagine doing that and think about what you would get as the leading term. What would its degree be? 4, yeah. Because when I FOIL these two, right, my highest power is going to be an x squared. And when you distribute this x squared to it, you're going to get an x to the 4th, right? What's my leading coefficient? Negative 1, yeah, negative. Because that's a negative x squared times this x squared that you get when you multiply those two. So negative x to the 4th is my leading term. So I saved myself an awful lot of work by just imagining that I was going to multiply them together and thinking about what the leading term would be. So what does that leading term tell me about the end behavior? What's it going to look like? Both down, yeah. Because even degree means the end behaviors are the same, both up or both down. Negative leading coefficient, down. Okay, so my end behaviors are both down. All right, how about even or odd? Is it even? How do you know? And in you to get an yeah, well you'd definitely have a cube term, and you have an x to the 4th term, so they're not all the same. Yeah, neither. Let's actually multiply it out so you can see what happens. Let's multiply it all out. So I have negative x squared, x plus 2, x minus 2, right? Oh, you're right, because the x term is going to drop out. Yeah, okay. So I get negative x squared times x squared minus 4, right? Distribute, and we get negative x to the 4th plus 4x squared. All my exponents are even, so I have y-axis symmetry. Good, thank you. Yep. So we also could have done all of this multiplication to get the leading term for the end behavior. Sorry, does everybody have it? Okay. All right, so I know it has y-axis symmetry, and the maximum number of turning points in this case would be 3 because the degree is 4. So I could have none, 1, 2, or 3. You're right, I can't. Yeah, I could have 1. I can't have none because that means my end behavior would have to look like that. All right, so I put in my end behavior. You're right, because we have to have one on 0. Yeah, maybe not. Yeah. All right, so there's my end behavior. My zeros are at 0, -2, and 2. So already, oops, I just put that on 3. Already, if I didn't know because I looked at the exponents, this is already looking like it has symmetry, right? So that should be a little hint to you. And then the outer 2 zeros go through the axis because they're multiplicity 1, and the middle one bounces, yeah. So this one's going to go down and meet the end behavior. That was bad. I'm going to erase these so I can get a better, so I can connect them better. That goes like that, and that goes like that, and they go through. This one bounces. Looks like that. Yeah, they look pretty symmetrical, right? That's a little better. And how many turning points do I have? 3. Good. All right, you try one. I've given you a polynomial in factored form. Sketch its graph. All right, so they gave it to us in factored form. That makes finding the x-intercepts or the real zeros easy, right? So we get x equals 0, x equals 3, x equals -2. What are my multiplicities on those zeros? 1. Good. So let's see, I've got -2, 0, and 3 as my x-intercepts. My y-intercept, I just plug in a 0 and I get 0. For end behavior and for symmetry, it's helpful to have this thing multiplied out. So if I were to multiply this, I would get x squared minus x minus 6, and then distribute in x, so I get x cubed minus x squared minus 6x, right? Okay. So my end behavior, based on the leading term, would be what? So one arm up, so I'll just start from the 0, and that one goes up, and this other arm goes down from the outermost 0. And then my zeros all have multiplicity 1, so that means that the graph has to go through the axis. So this has to go up, down, and back up to finish the graph. Yes, the maximum turning points is 2. I have 2, so I haven't made a mistake. If I got 4 turning points, I would say to myself, I must have drawn this wrong because I can't have more than 2. That's really all that that's for at this point. Does this have any symmetry? No. It actually looks like it has symmetry the way I drew it, which means that that's just because I can't be more accurate. This might go like this, you know, and like this. And now it doesn't look symmetric anymore. Oh, yeah, right. And this one's at -2 and that one's at 3. And I could have known that there was no symmetry because all of my exponents are not even or odd. So this is no symmetry. All right, so now I'm going to have you work in your groups on this little activity. Sketch a graph of a polynomial that satisfies the conditions. So there can be many graphs, many different graphs that will satisfy the conditions that I give. So you just need to discuss, look at each other's graphs, and decide if each of them satisfies. Yeah, Katrina. For number 4, I said degree 4 with 4 turning points. So what would you say about that? That's impossible. Can't have a degree 4 with 4 turning points. Maximum it could have is 3.